Hello and welcome to another mathematics video in which we seek to analyze and solve ordinary differential equations. And as you can see in equation 1 here, we have yet another non-linear differential equation. Non-linear because its dw by dx term is all squared. Now you'll see here that this is a simple model for the shape of a tsunami where w as a function of x is the height of the wave relative to a distance x offshore. So the question is, how do we solve equation 1? Well, let's make a start and see what we can do to make an attempt to solve this equation. I'm going to start on another page. So basically, in fact, at this stage, I'll just cut and paste equation 1, and then I don't have to rewrite it out again. And we'll move that to there and make a start. So basically, what I'm going to do is I'm going to take the square root of both sides of equation 1 so that we get 1, let me just get the right pointer, so that we get 1 over the square root of 2 dw by dx, and that's equal to the square root of 2w squared minus w cubed. Now, you can probably see that we can actually factorize out w squared inside the radical sign. So actually what we get is a square root of w squared times 2 minus w, right? So what we've now got is 1 over root 2 dw by dx equal to, well, this can be split up into the square root of w squared times the square root of 2 minus w. And you can see that I've written the square root of 2 minus w as 2 minus w in brackets raised to the power of half. So it might become more apparent why I've written that like that at this stage. It's just a little bit easier than writing two square root terms multiplied together. So basically, the square root of w squared is just w, and we'll put the square root radical sign back in here, and that is a square root of 2 minus w. So we'll call that equation 2, right? Now then, we can separate the variables. So I'll write that out, separate the variables. To get dw over w times the square root of 2 minus w, and that's equal to the square root of 2 times dx, and of course we want our integral signs in there like that. Now let's go to the next page. So what we've got is dw, it's actually the integral of dw over w 2 minus w to the power of half. So I'm rewriting it like that again. Sorry about the switching back and forth from the power of a half to the square root sign. It doesn't really matter. It's whatever you're comfortable with. and that's equal to square root 2 times the integral of dx. Now, what we say is we let u be equal to 2 minus w. So basically, my thinking is that we need, instead of having a dw like that over a 2 minus w to the power half term, which is hard to solve on its own, if we can convert the denominator here into something like u to the power half and then du on top, then it's going to be a lot easier to solve that integral. So let's continue with what we're doing here. We'll just, when I can find my pointer, we can ascertain that du is equal to minus dw, right? And also w is equal to 2 minus u, right? So we substitute these terms back in to the left-hand side of this equation. I can't remember what equation I call that, so we'll call it equation 3, right? Okay, so we've got from this dw is equal to minus du, right? So under the integral sign, we've got minus du divided by w, which is 2 minus u in brackets, multiplied by u to the power of half. And that's equal to root 2 times dx. Okay, so we'll call that equation 4. It doesn't look great. It need to make that look more like an arrow, I suppose. So we've got the square root of minus du over 2 minus u to the half here on the left hand side equal to root 2 times the integral of dx on the right hand side. Now, I've actually noticed an error in my own notes here because I've missed out a minus sign. So I'm going to have to try and rectify that error as we work through these online slides, which I'm recording now. So we've got a minus sign here. What I'm going to do is I'm going to multiply both sides of equation 4 by minus 1. So first of all, let's cut and paste equation 4. Add to new page. Right. So we can write the integral of du over 2 minus u to the half equals minus root 2 times the integral of dx. And I'm not going to put the constants in just yet, but what we're going to do is we're going to do another substitution. So now, and I'll write this in red, now write p equal to u to the power half, so that dp equals one moment, let's just go back. So if we square p, we've got u equal to p squared, right? So squaring both sides of this we get this, right? And then it's a lot easier to differentiate this term on both sides to give, let me see, where are we now, right? And we're right, and du equals 2p dp. My writing is getting very scrawly there. Okay, so let's cut and paste all of that onto a new page. Right, okay. So we've got du, well, du is 2p dp. So we've got 2p dp over, what have I said? 2 minus, well, u is p squared, so it's 2 minus p squared. And then times u to the half, and I've said u to the half is p. And that's equal to minus root 2 dx, okay? Now, let's give that a name. We'll call it equation 5. I have to look at that previous equation again because it's immediately gone out of my mind. Right, okay. So, what we might be able to see from this equation, well, maybe I should use red, is that the p in the numerator cancels with the p in the denominator. So now what we've got is the integral of 2 divided by, and I'm going to write the denominator as the root of 2 squared. Well, actually, before I do that, just let me write it as it was on the other page with the p cancelled out. So we've got 2 minus p squared, 2 minus p squared, and that's dp. And that's equal to minus root 2 times the integral of dx, minus root 2 times the integral of dx. So, yeah, I'm just double checking everything. So now we're going to rewrite this as 2 over the square root of 2 all squared minus p squared. And then we put the dp in there, equal to minus root 2 times the integral of dx. And I think this will be equation 6. Yeah. So now what we can do is we can say, this is another substitution. So let p be equal to root 2 times a hyperbolic tangent of theta. And the reason why I've chosen root 2 tan theta is because we want a root 2 all squared here so that we can factorize it out of the denominator. So anyway, before we do that, we see that dp is equal to root 2 shec, or hyperbolic secant, squared theta d theta, right? So let's cut and paste that because I'm not going to have quite enough room to do what I want to do. So add to new page. Okay. Let's go back to black. So now what we've got is the integral of 2 times dp. Well, we know dp is equal to this on the right hand side of that equation. dp is equal to that. So we've got 2 root 2 sec or hyperbolic secant of theta d theta, all divided by root 2 squared minus, well, it's going to be p squared, so that's going to be root 2 squared, which we know is 2, but we'll keep it as root 2 squared for now. And the reason is that we've got this as root 2, so we want to keep everything roughly the same. And we've got minus the hyperbolic tangent squared theta there, and that's equal to minus root 2 times the integral of dx. I wish I could draw straight lines. It's not at all easy on these electronic pads, and I like it to be reasonably legible and readable. So anyway, we've now got this expression on the left hand side. So once again, let's cut and paste equation 7. Right, let's just ink that back in. So we can simplify everything on the left hand side. So we've got the integral of 2 root 2 hyperbolic secant squared theta d theta, and that's divided by let me get a like slightly straighter line there. Right, okay, so we can take out the root 2 squared, and I'm just going to call that 2, multiplied by, in brackets, 1 minus tan squared theta, right? And that's equal to minus root 2 times the integral of dx. We'll call that equation 8. Now, I'm going to do another cut and paste. My writing seems to be getting bigger, leaving less space upon which to write. Anyway, never mind. Add to new page. So on the left hand side, you can see that since 1 minus tan squared theta, that's a hyperbolic tangent, squared of theta, is equal to the hyperbolic secant squared of theta, which again I call sec squared theta. We can substitute this in for this, so that we get well, we've got, we can cancel a 2 and a 2 there, can't we? So what we've got is outside the brackets we've got 2 times inside the bracket sec squared theta d theta, all divided by sec squared theta. And actually, yeah, I think that's okay. Yeah, and that's equal to minus root 2 times dx. We'll call this equation 9. So you can see that on the left hand side we've got basically root 2 times the integral of sec squared theta d theta over sec squared theta, equal to, on the right hand side, minus root 2 times the integral of dx. So as you can see, the sec squared theta cancels with the sec squared theta in the denominator. So let's just get rid of this stylus. So what we're left with is root 2 times the integral. I'm not doing these integral signs very well, am I? Right, integral of d theta equals minus root 2 times the integral of dx. And we'll call that equation 10. Right. So that's actually quite a simple integral, isn't it? By the way, at this stage, do not cancel these root 2s. They're important. And the reason is that what I haven't put in up until now, and this is kind of optional at this stage because we haven't actually done the integral on the right-hand side. But what a lot of authors do is they add in the constant early on before they've even done this integral. So that's why we can't really cancel the root of -2 at this stage. So let's just go back to the stylus and cut and paste this equation, which we're going to call equation 10. Right, well, I ought to really change to black ink there if I can find the pointer. So we'll call that equation 10. Is that right? Did it have equation? Yeah, they have an equation 10. So straight off the bat, we can integrate this to give root 2 theta. Make that look more like a root 2. Tell you what, let's just start again. Root 2 theta equals minus root 2 times x plus a constant. Okay, so well, what we can do is I'll stick to what I've done in my notes, even though somewhere I've lost the minus sign. We know, and I'll write it in red, we know that we use a substitution, p equals root 2 tan theta, right? So this means that if we divide both sides by root 2, then we get tan theta equal to p over root 2. And then what we can do is we can take the inverse tangent of both sides, or the inverse of hyperbolic tangent of both sides, to get the following. Right? Whoops. No, let's get this right. Right, okay. There. So theta is equal to the inverse hyperbolic tangent of p over root of 2. So we've got over here, let's change to green. So we've got the root of 2 times the inverse hyperbolic tangent of p over root 2. That should really be in brackets. And that's equal to minus root 2 times x plus c. Right. We'll let's just we'll just write it in green. There we are. So that's equation 11. Okay. So where do we go from here? Well, first of all, I'm going to cut and paste that. Okay. Right. Cut and paste that and start to simplify it. So now what we've got is if we divide both sides by root of 2, we get the inverse hyperbolic tangent of p over root 2 equal to, let me see, I'm going to write it as c over root 2 minus x. So as you can see, I've divided both sides by the square root of 2. So it gets rid of the square root of 2 there, but we're left with minus x plus c over the square root of 2. And in actual fact, I think what I did here was leave that as it was. So, okay, we've got this. Now, if we take the hyperbolic tangent of both sides of what we will call equation 12, then let me just write this again. I'm going to cut and paste it. Just I don't know if I can cut and paste it down below. It might not work. So let's write it out again. So we've got the hyperbolic tangent, the inverse hyperbolic tangent of p over root of 2 equal to, and we'll leave a bit of a space, c over root 2 minus x. Right, why have I left a space on both sides of this equation, which we'll call equation 13? Well, that's because if I can find my pointer, I'll choose blue this time. We're going to take the hyperbolic tangent of both sides of equation 13. Put it in square brackets. So hyperbolic tangent of both sides of equation 13. So what this does on the left hand side is it leaves us with just p over root of 2. The tangent, the hyperbolic tangent of the inverse hyperbolic tangent is what is it just cancels basically to put it mildly, and what you're left with is whatever is here. So that's the best explanation I can put at the moment without going into great detail. But anyway, so what we've got is, if we go on to another page, we've got well, I need to write in black, don't I? So let's just change to black. So we have p over the square root of 2 equal to the hyperbolic tangent of c over root of 2 minus x. Okay? So let me see. So therefore, p equals the square root of 2 times a hyperbolic tangent, or tan if you like, of c over root of 2 minus x, close bracket. And where did we get up to in terms of equation labels? Well, we got up to equation 13 there, so we'll call this equation 14, right? But where's my pointer gone? But see, it keeps disappearing. So there we are. But p equals u to the power of half. And we know, well, let's just substitute u to the power of half into equation 14. So we've got u to the power of half equals the square root of 2 times the hyperbolic tangent of c over root of 2 minus x, and we'll call that equation 15. Right, okay. Well, that doesn't look like a 5, does it? Let's just write a more legible 5 in. Okay, so we've got that. Now, I'm going to cut and paste it once again. Right. Let's just put the brackets in more clearly. So when I can find my pointer, and it does keep disappearing. Anyway, so we can square both sides of equation 15, right? To get u equals, well, root 2 squared is just 2 times the hyperbolic tangent squared of c over root 2 minus x. Okay? And we also know, now we'll call that equation 16. So we've got another buts coming up, but u equals 2 minus w, if you remember. So let's just go all the way back. There we are. So, well, is that right? Is that where we are? Or do I have to go back even further? Yeah, so here we've got u equals 2 minus w. Do you remember when we were using the first of our substitutions in equations 3 and 4? So if you go right back to where we are, we can substitute u equals 2 minus w to get, and I'll go on to another page. So we've got 2 minus w is equal to, and I have to go back on this, equals 2 than squared. Oh, dear me. And I'm actually going to write the bit in the brackets a slightly different way, because I think that's the way a textbook answer would be. So that would be minus x plus c over root 2, like that. Okay? So we'll call that equation 17. Okay? So now w is equal to, so if you add w to both sides of equation 17 and subtract all of this from both sides, then we get w is equal to 2 minus 2 times the hyperbolic tangent squared of minus x minus c over root 2, like so. Now, what I'm going to do is just tie up a few loose ends, because that is basically the solution. But what the book does is it tidies up this constant term here. I think in the book it might be a plus sign here, or so anyway, what we're going to do is we're going to write w is equal to, we're going to factor out the 2 times 1 minus than squared in brackets minus x minus root 2c over 2. There we are. and that is not the final form I want to put it in. We want to take out this factor of 2 on the bottom, so we get W is equal to 2 times, in brackets, 1 minus hyperbolic tangent squared of a half minus a half times x minus root 2c. Okay, and that is the solution. So let's just double check. Yeah, so basically we've just tidied up what we have here in the argument, I guess you would say. We've just factored out this this 2 in the denominator to get a half here times x minus 2x minus root 2c. So that is a solution for the shape, or the general shape, of a tsunami wave a distance x away from some point in the sea offshore. And that, as they say, is that for that question. I call that equation 20, just so that you have some reference for it. And that's the solution. So I hope you've learnt something from this video, and that you will return to watch more of my sessions, my mathematics sessions and videos. So until then, I bid you farewell and take care for now. Bye.